Hello everyone, myself Surya, a final year student from Tech Multitech Dr. Rangarajan Dr. Sakuntala Engineering College. This is my final year project and the title goes on like Bacterial Contamination Monitoring and Prevention in Chambers using Post-Processing Techniques. So let's go into the project. So this is my objective. So according to my objective, the system offers advanced cleaning process to significantly elevate bacterial chamber hygiene, surpassing traditional methods. It incorporates a semi-automatic control system for bacterial chamber management, enhancing operational efficiency and safety. It includes a post-processing unit to further refine cleaning procedures, ensuring through a decontamination and minimizing health risk. It addresses health concerns associated with bacterial testing by employing advanced cleaning technique and safety measures. The core system boasts comprehensive processing capabilities, delivering true and reliable results for bacterial chamber cleaning. Now we are going to see about existing system and its methodology. According to the World Health Organization recommendations, it is essential to sanitize laboratory equipment and devices to maintain a sterile environment. The preferred method for sanitization involves using either 70% ethanol or a 10% bleach solution. So sanitation procedure goes as follows. Prepare a solution of 70% ethanol or a 10% bleach solution. Apply it to the surface of the equipment using a clean cloth or sponge. Ensure through coverage of all surfaces and allow the solution to remain in contact for the recommended contact time. Rinse the equipment with sterile water after sanitization, if necessary. Allow the equipment to dry air before use. References are given. It is WHO guidelines for laboratory equipment sanitization. Please refer to the link for further more information. So now I'm going to see about proposed system. Enhanced laboratory safety measures. So the purpose of this is to our proposed system introduce advanced safety measures to ensure the integrity of laboratory experiments and safeguard researches. The chamber design is specifically designed room that are equipped with bacterial specific control units actively preventing potential issues. The control units regulate a pressure within the chamber, preventing bacteria from escaping and maintaining a controlled environment. After testing, the heater and sterilizer are activated for a fixed duration. According to WHO guidelines, bacteria are rapidly killed at temperature of 149 degrees Fahrenheit or at 65 degrees Celsius, ensuring thorough sterilization. Now we are going to see about safety enhancements. By adhering to these protocols, our system prioritizes laboratory safety, minimizing the risk of contamination and ensuring the reliability of research outcomes. This highlights the proactive measures implemented in our system to promote a safe and controlled laboratory environment by fostering optimal research conditions. So this is my block diagram. The main controller for all this unit is ESP32 microcontroller. So we are for the communication part, I have connected it with a Bluetooth with a mobile app. With that app, I can control this microcontroller and rest of the other parts. So it is also recorded in a database. So for the chamber unit, we have pressure sensors like BMP 180, humidity sensor DHT 22, and also its separate temperature sensor. For heat and sterilizing unit to do the work, we have UVC sterilizer, which is a UV light, and PTC heater with a heat sink and heat separator fan. We also have a DC pump vacuum motor to vacuum that contaminated area. We also given a relay, and we have all connected this with a control unit which is controlled by a smartphone. So this is my literature survey. So according to the first author, the pros of his papers are that it specifies study of UVC, so which I have implemented in my project, and its cons is that light does not reach everywhere. And the second pros is that identifying inactivation of microorganism, and its cons is no post processing. The third is optical spectroscopy, and its cons is it's only detect the bacteria. So this is the parameters of my bacteria uh, for testing. So according to bacteria Entamoeba coli, it is also known as E. coli, and the testing temperature is 37 degree. The killing temperature is above 60 degree, and the UVC sterilization timing is it should be above 60 degree within a time duration of 10 to 30 minutes. As for Salmonella typhi, or also known as typhoid causing bacteria, so this bacteria testing temperature is 37 degrees Celsius, and the killing temperature is above 60 degrees Celsius, and it should be maintained at 60 degrees Celsius for a duration of 10 to 30 minutes. So the same goes for Mycobacterium tuberculosis bacteria, Streptococcus pneumoniae bacteria, and Lactobacillus bacteria also. So the every bacteria goes with the same testing temperature of 37 degrees Celsius, and its killing temperature is 60 degrees Celsius, and this degree Celsius is maintained from a duration of 10 to 30 minutes within the UV light. So this is my circuit board. You can see a heat sink and a motor, which is also controlled and connected with the ESP32 controller, and we also have given a relay, and this is the motor for the vacuum. So you can see the overall circuit here with a clear explanation. I have also attached a UVC light at one end of the uh, chamber. So what are the problems faced here? In the beginning stage, tested with the BMI 280 pressure sensor, the sensor didn't give the accurate value of the pressure. So instead of BMI 280, I changed it to BMI 180 in this project. The output value relatively good compared to BMI 280. In further, there's a library clash occurs in DS18B20 temperature in combination with pressure sensor. So the internal temperature sensor in DHT22 has been used to test this chamber temperature. So how it works? First, we are going to activate the system. So upon activation, the system reads the current date and initializes the chamber into testing mode according to predefined preferences. The pressure and temperature sensing are employed by BM180 sensor to detect the pressure and temperature within the chamber. The BM180 sensor is a biometric pressure and temperature sensor featuring an 12C uh, interface, and it ensures accurate and reliable data collection. For humidity calculation, I go with DHT22 sensor. It is utilized to calculate the humidity levels within the chamber. This sensor provides precise humidity readings, aiding in comprehensive assessment of chamber conditions. So now we are going to see about vacuum pump integration. A vacuum pump integration is integrated within the chamber to lower the internal air pressure. This process creates a low pressure environment within the chamber, inhibiting the movement of bacteria through air. Now we are going to see about the heating elements. So the heating element is positioned inside the chamber. The heating element maintains a critical temperature to lethally eradicate the bacteria, that is the 60 degrees Celsius, more than 60 degrees Celsius, within a time duration of 10 to 30 minutes. So meeting WHO standards post testing. I've already mentioned that I have attached a UVC light to produce UV. So it is integrated with UVC lights, complementing the heat element, providing additional bacterial elimination capabilities. Now we're going to see about control unit, that is ESP32, and it is located externally. The control unit enables convenient operation and monitoring of the sterilization process, ensuring precise control over temperature during other parameters. So for that, I have used a mobile phone. I will show you that. So this is the out screen of my mobile phone when I'm operating. So as you see, the status is connected, and we can also see the chamber status and bacteria list. For the chamber status, we are seeing the current chamber temperature is 34.80, and the chamber pressure is 1009.15 HPA, and the chamber humidity is 64.90. For the testing bacteria list, I have given the testing mode. like Entamoeba coli, Salmonella typhi, Streptococcus pneumoniae, Lactobacillus, Mycobacterium tuberculosis. I have listed there the 6 bacteria. And for the control commands, 7, 8, 9 A, B, C. As you see, each commands represent heater on or off, UVC on or off, pump on or off. So at the bottom I have given a dialog box like enter the input and send. So if you given 7 as the input, and if the command is given 7, and if when it is sended, the chamber will activate the heater and wait till the command gets over. Okay, now this is the BUM 180 pressure sensors output. So why ESP32? The ESP32 features a dual-core 10 silica extensa LX6 microcontroller, which can be programmed using the Arduino IDE, MicroPython, or ESP IDF, the Expressive IoT Development Framework. CPU speed: each core in ESP32 can operate at up to 240 MHz. Its wireless connectivity is built in Wi-Fi, that is 802.11 B or G or N, and the Bluetooth we have been used is a classic low energy BLE. Its capabilities: it supports a wide range of wireless security protocols including WEP, WPA, WPA2 and WPS. Its memory comes with 520 KB of SRAM and 4 MB of flash memory. Although there are variations with more memory, then its general input and output pins. For ESP32, it has a very large number of general purpose input or output pins, typically 25 to 38 pins, which can be used for various purposes including digital input or output, analog input, PWM, I2C, SPI and more. The peripherals are listed here. For ESP32, it includes a wide range of peripherals such as UART, I2C, SPI, PWM and more, making it versatile for interfacing with various sensors and devices. So these are the references I have enacted here. You can see. Thank you.